All right, so you're here because, let's be honest, you want a shortcut
Shortcut, yeah.
to understanding complex topics
Right.
without having to wade through like a mountain of, dense academic papers.
Oh, yeah, absolutely.
And today we're going deep on natural language processing,
NLP.
NLP with transformers, and this deep dive is going to be based on the book Natural Language Processing with Transformers.
Great book.
Now,
It's it's fascinating.
yeah, it's been a real. I find it fascinating how transformers have really kind of come to dominate
Oh, yeah.
NLP in just the last 6 years.
Yeah, since about 2017, they've just
Yeah.
exploded and become like the go-to architecture for pretty much any NLP task that you can think of.
Yeah, and the book even starts with this kind of striking analogy of language as being these sort of like airborne,
Pages brain germs?
yeah, these contagious brain germs. It's kind of a disturbing image.
Yeah.
But it really, I think it underscores how fundamental language is to how we think.
Absolutely. It's how we spread ideas. It's how we communicate. It's how we understand the world.
Yeah, so our mission today is to really distill,
Okay.
what are these transformers? How do they work?
Yeah.
And what kind of amazing things have they made possible in NLP?
Let's do it.
So let's kick things off by going back a little bit before Transformers.
Okay.
Before the Transformer Revolution, there was this architecture called the encoder-decoder framework,
Okay.
which was kind of the state of the art for a lot of NLP tasks.
Yeah, it was very popular, very effective for things like machine translation.
Yeah, so can you give us just a quick overview of how that works?
Yeah, so imagine you want to translate a sentence like Transformers are great into German,
Okay.
which would be Transformers sind großartig.
Okay.
So in the encoder-decoder framework, what happens is the encoder takes the input sentence like Transformers are great,
Right.
processes it word by word, and then condenses all of the meaning of that sentence into a single fixed length vector.
Oh.
It's almost like a summary, a very dense summary of the entire sentence.
So like a really, really potent representation of the core idea of the sentence.
Exactly. Yeah, it's like distilling the thought down into a single point.
Okay.
And then the decoder takes that dense representation, that meaning vector,
Okay.
and uses it to generate the output sentence word by word.
Okay.
So in this case, it would take that meaning and then start generating transformer,
Right.
sind großartig, and so on.
So the encoder is digesting,
Yeah.
and then the decoder is constructing based on that digested meaning.
Yeah, that's a good way to put it.
Okay, so that's the encoder-decoder framework.
Right.
Now, Transformers kind of came along and changed the game.
They did.
And one of the key shifts that they enabled was this idea of transfer learning,
Yes.
which had already been very successful in image processing, but hadn't really taken off in NLP in the same way.
Right.
So can you explain how transfer learning works and why it was such a big deal?
Yeah, so traditionally in machine learning, what we would do is we would train a model for a specific task.
Right.
And we would start from scratch, and we would need a large labeled data set for that specific task.
Okay.
So if you wanted to do, let's say, sentiment analysis, you'd need a large data set of text labeled with positive or negative sentiment.
Okay.
If you wanted to do something else like named entity recognition,
Right.
you'd need a different data set labeled with the named entities.
Right.
So it was very task specific and it required a lot of data.
Yeah.
Transfer learning changes that because the idea is you first pre-train a model
Okay.
on a massive general purpose data set.
Okay.
So in image processing, this might be something like ImageNet,
Right.
which has millions of images
Right.
with different labels.
Okay.
And by training on that data set, the model learns to extract general features
Okay.
like edges and shapes and textures.
So it kind of develops this foundational understanding of the world of images.
Exactly.
Okay.
And then what you do is you take that pre-trained model
Right.
and you fine-tune it
Okay.
on a smaller task-specific data set.
Right.
So, for example, you could take that ImageNet pre-trained model
Okay.
and then fine-tune it to classify different types of birds.
Okay.
And because it already understands edges and shapes and textures, it can very quickly learn the specific features that distinguish different bird species.
Right. It's like it's already got this basic art training, and now you're just teaching it how to paint portraits or landscape.
Exactly. It's a really good analogy.
Okay, so this is how transfer learning revolutionized image processing.
Yeah.
And then something similar started to happen in NLP, but with a bit of a lag.
Yeah. It took a little while for NLP to catch up.
Right.
So before around 2018, transfer learning in NLP was mostly focused on word embeddings,
Okay.
which were these dense vector representations of individual words.
Okay.
But the problem with those was that they were contextless.
Right.
So the word bank would have the same representation whether you were talking about a river bank or a financial institution.
Right, right.
And then around 2018, we started to see the emergence of these full-blown language models
Okay.
that could be pre-trained on huge amounts of text
Right,
and then fine-tuned for a variety of NLP tasks.
right.
And this really changed the game because now you had these models that had a much deeper understanding of language.
Right.
And they could be adapted to new tasks much more effectively.
So instead of training from scratch every single time, you're now building on top of this foundational understanding of how language works.
Exactly. Yeah.
Yeah.
Like we humans, we learn grammar, vocabulary before we start learning how to write specific types of documents.
Right, right.
And these language models are doing something similar.
Okay, so we've got this foundation of transfer learning.
Yeah.
Now let's actually look under the hood
Okay.
at the transformer model itself.
Right.
What is it about this architecture that makes it so powerful?
So the key innovation in transformers is the attention mechanism.
Okay.
And to understand attention, it's helpful to think about how we humans read a sentence. We don't pay equal attention to every word.
Right, right.
Some words are more important than others for understanding the overall meaning.
Right.
And attention mechanisms allow neural networks to do the same thing.
Okay.
They can assign different weights to different parts of the input sequence.
So it's like the model has the ability to highlight certain words.
Exactly. Yeah, it's like it's focusing its attention on the most relevant parts.
Okay.
And a particularly powerful type of attention is self-attention.
Self-attention.
And this is where things get really interesting.
Okay.
So in self-attention, the model is calculating these attention weights by looking at all of the hidden states within the same input sequence.
Okay.
So for example, if you have the sentence, transformers are great,
Right.
the self-attention mechanism allows the word transformers to attend to are and great and vice versa.
Okay.
And it figures out how those words are all related to each other within that specific context.
So every word gets to kind of look at all the other words at the same time.
Exactly. Yeah, it's like they're all having conversation with each other.
Right.
And this ability to capture these long-range dependencies
Mm-hmm.
is really crucial for tasks like understanding sentiment
Right.
or resolving pronouns.
Okay.
Because you need to be able to connect words that are far apart in the sentence.
Yeah, you can't just be looking at the words that are right next to each other.
Right.
You need to be able to see the whole picture.
Exactly.
Yeah.
And self-attention allows the model to do that.
Okay, so we've got self-attention,
Yes.
which is allowing the model to weigh the importance of different words.
Yes.
Now, there's another important piece of this puzzle,
Okay.
which is how the model actually keeps track of the order of the words.
Right.
Because if you just have a bag of words, great are transformers,
Yeah.
means the same thing as transformers are great.
Exactly. Yeah, the order is really important for meaning.
Yeah.
And so that's where positional embeddings come in.
Positional embedding.
So these are vectors that are added to the word embeddings to give the model information about the position of each word in the sequence.
Okay.
So there are different types of positional embeddings.
Okay.
You have absolute positional embeddings, which essentially say, okay, this is the first word, this is the second word, this
Yeah.
is the third word,
Right.
and you have relative positional embeddings, which focus more on the distances between words.
So like this word is 2 words before that word.
Exactly.
Yeah.
So instead of saying this is the 5th word, it's
Yeah.
saying this word is 2 words before the 7th word.
I see.
And this can be more informative in some cases because the relationships between words are often more important than their absolute positions.
Right. It's more about like the local neighborhood.
Exactly.
Okay, so we've got word embeddings, we've got positional embeddings, we've got self-attention.
No.
All these things are coming together
Yeah.
to give these transformers their power.
Yeah. It's a really elegant architecture.
Okay, so the book also dives into this whole Hugging Face ecosystem,
Mhm.
which seems to be like really essential for actually using these models in practice.
Absolutely.
So where does Hugging Face fit into all of this?
So the Hugging Face Transformers library is like this amazing toolbox
Okay.
for anyone working with transformers.
Okay.
So it provides a standardized way to access and use hundreds of different pre-trained transformer models.
Hundreds.
Yeah, there are tons of them.
Wow.
And this is huge because it means you don't have to build each model architecture from scratch.
Right, it's like a giant library of pre-trained models.
Exactly, yeah. It's like a model zoo.
Right.
And it supports all the major deep learning frameworks.
Like,
PyTorch, TensorFlow, JAX.
okay.
So you can easily switch between them depending on your preference.
Right, so you're not locked into one specific framework.
Right.
Okay.
And it also provides task-specific heads,
Task-specific
which are
habits.
basically additional layers that you can add on top of the core transformer model to
Okay.
fine-tune it for specific tasks.
Right, like classification or
Yeah, exactly.
question
Yeah,
answer.
entity recognition, all sorts of things.
Okay, and so this must save like a ton of time and effort.
Oh, yeah, absolutely.
Like you don't have to reinvent the wheel every time you want to try a new model or a new task.
Exactly, and it really lowers the barrier to entry
Right.
for researchers and practitioners who want to work with these models.
Okay, so that's the Transformers library.
Right,
But Hugging Face is more than just that.
right. They have a whole ecosystem.
Yeah.
So they also have the tokenizers library,
Okay.
which handles the process of breaking down text into tokens.
Right, because the models can't work with raw text. They need it to be tokenized.
Exactly. Yeah, they need it to be in a numerical format.
Right.
And then they have the datasets library,
Okay.
which makes it very easy to load, process, and manage large datasets.
So they've really thought of everything.
Yeah, they've really made it very user-friendly.
Okay, so we've got the tools.
Yes.
Now let's actually talk about some of the cool things you can do with them.
Okay.
So text classification is a very basic,
Yeah, a fundamental NLP task.
fundamental task.
Yeah.
And the book uses this example of classifying the emotional states of tweets.
Right.
So how would you actually use transformers to build a system that could do that?
So you can imagine having a data set of tweets,
Right.
and each tweet is labeled with an emotion like anger, joy, sadness.
Right.
And then you would use the Hugging Face ecosystem to build a model that could predict those emotions for new tweets.
Okay, so walk me through the steps.
All right, so first you would use the datasets library
Okay.
to load your labeled tweet data.
Okay.
Then you would use the tokenizers library,
Oh.
specifically the auto tokenizer,
Okay.
which can automatically load the correct tokenizer for a given pre-trained model.
So you don't even have to choose the tokenizer, it just does it for you.
Exactly.
Yeah.
That makes it very convenient.
Okay.
And then you would use the transformers library to load a pre-trained model, like
Okay.
Distillbird, for example,
Distillbird.
which is a smaller, more efficient version of BERT.
Right, we talked about that a little bit earlier.
Yeah.
Okay.
And this model would already have a classification head attached to it.
Okay.
And then you would fine-tune this model on your tweet data.
Okay, so you're taking this pre-trained model
Right.
that already understands language generally,
Yeah.
and you're just fine-tuning it to this specific task of recognizing emotions in tweets.
Exactly. And because it already understands language so well,
Mhm.
it can learn this new task much more quickly.
Right, right. It doesn't have to start from scratch.
Exactly.
Okay, so that's text classification.
Yeah.
Now let's talk about text generation,
Yeah.
which seems like a whole other level of complexity.
Yeah, it's a very different task.
Yeah.
So the book talks about models like GPT-2,
Okay.
which are specifically designed for text generation.
Okay.
And the way they work is they're trained to predict the next word in a sequence.
Okay.
So you give them a prompt, like a starting piece of text,
Right.
and then they predict what the next word should be. And then you add that word to the prompt, and then you predict the next word, and so on.
So it's like an autocomplete on steroids.
Yeah, exactly. It's like a super-powered autocomplete.
Right.
But the challenge is, how do you make sure that the generated text is actually coherent and meaningful?
Right. Because it could just be like a random stream of consciousness.
Yeah, could just be gibberish.
Right.
So the decoding strategy that you use is really important.
Decoding strategy.
So this is how you choose the next word,
Okay.
based on the probabilities that the model outputs.
Okay.
So a simple strategy is greedy decoding, where you just pick the word with the highest probability.
Okay.
But that can lead to repetitive and kind of boring text.
Right. It's like always taking the most obvious next step.
Exactly.
Yeah.
So there are more sophisticated strategies that consider multiple possibilities,
Okay.
like beam search,
Okay.
which keeps track of several promising sequences.
Right. So it's like exploring multiple paths simultaneously.
Exactly. Yeah.
Okay.
And there are also sampling-based methods,
Okay.
like temperature scaling,
Temperature scaling.
which adjust the randomness of the output.
Okay, so you can make it more creative or more predictable.
Exactly. Yeah. You can control how much surprise you want.
Okay, so it's like a knob that you can turn to control the creativity of the output.
Yeah, that's a good analogy.
Okay, so that's text generation.
Yeah.
Another really interesting application that the book talks about is text summarization.
Right.
So how do transformers approach the problem of taking a long document
Yeah.
and condensing it down to its essential points?
So this is a challenging task because it requires the model to understand the meaning of the text
Right,
and then generate a shorter version that captures the most important information.
right.
And the CNN Daily Mail data set is a common benchmark for this task.
Okay.
And what's interesting about this data set is that the summaries are often abstractive,
Abstractive.
which means they're not just copying sentences from the original article.
Okay.
They're actually paraphrasing and synthesizing the information.
Right. So it's not just like pulling out the key sentences.
Exactly.
It's actually understanding the meaning and rewriting it.
Yeah, it's a much higher level of understanding.
Okay.
And the row score is a common metric for evaluating summarization models
OG?
because it focuses on recall, which is how much of the important information from the original text is present in the summary.
Okay. So it's not just about fluency. It's about actually capturing the key ideas.
Exactly.
Okay. And the book mentions the Pegasus model
Right.
as an example of a transformer that's specifically designed for summarization.
Yeah, Pegasus is really interesting because it's pre-trained in a way that's very similar to how summarization works.
Okay.
So during pre-training, it's given a document with some sentences masked out,
Oh.
and it has to learn to generate those missing sentences.
So it's like a fill-in-the-blank exercise.
Exactly, yeah.
Oh, okay.
And this helps it to learn to identify and focus on the most salient information.
Right, because it has to figure out what's missing.
Exactly.
Okay, so that's Pegasus for text summarization. Yeah.
Now let's talk about question answering,
All right.
which also seems like a really good fit for transformers.
Yes. Yeah, definitely.
Because of their ability to understand context.
Right.
So how would you use a transformer to build a system that could answer questions based on a given document?
So the most common approach is extractive question answering,
Extractive.
where the answer is a span of text within the document.
Okay.
So you have a question and you have a document.
Right.
And the model has to identify the start and end positions of the answer within that document.
Okay.
So it's essentially highlighting the relevant part of the text.
Right. So it's not generating an answer. It's finding the answer that's already there.
Exactly. Yeah. It's like a very precise search function.
Right.
And one challenge is that documents can be very long.
Right.
So the answer might be far away from the beginning.
Yeah.
So to handle that, we often use a sliding window approach.
Sliding window.
Where we break the document up into smaller chunks,
Okay.
and then we process each chunk separately.
And then we combine the results.
Okay, so it's like looking through the document with a magnifying glass.
Exactly.
You
Yeah.
know,
And the Haystack library is really useful for building question answering systems
Haystack.
because it provides components for both retrieving relevant documents
Okay.
and then extracting the answer from those documents.
So it's like a two-stage process.
Yeah,
You first find the right document, and then you find the right answer within that document.
exactly.
Okay.
And for retrieval, you might use something like keyword search or dense passage retrieval,
Okay.
which is a more semantically aware approach.
Right.
And then for the actual answer extraction, you would typically use a transformer model.
Okay, so transformers are being used in both stages.
Yeah, they can be used in both stages.
Okay. And how do you actually evaluate the performance of a question answering system?
So for retrieval, you typically use recall,
Okay.
which measures how often the correct document is retrieved.
Okay.
And for answer extraction, you might use metrics like exact match, which checks if the predicted answer is exactly the same as the actual answer,
Right.
or the F1 score,
Sheriff one score.
which considers both precision and recall.
Okay.
And the book also mentions generative question answering,
Generative.
which is where the model actually generates the answer instead of just extracting it.
Okay.
But that's generally considered a more difficult task.
Right, because now you're not just finding the answer, you're creating it.
Exactly.
Okay, so we've talked about a lot of really cool applications of transformers.
Yeah.
But the book also gets into some of the more practical challenges
Okay.
of actually using these models in real-world settings,
Yeah.
like efficiency.
Efficiency is huge.
Yeah.
Because these models can be very computationally expensive,
Right.
and they can take up a lot of memory.
Yeah, and if you're trying to deploy them on a device like a smartphone,
Yeah.
or if you're trying to serve a lot of users at the same time,
Right.
you need them to be as efficient as possible. So what are some of the techniques that people are using to make transformers more efficient?
So one technique is knowledge distillation,
Knowledge distillation.
where you train a smaller student model to mimic the behavior of a larger teacher model.
Okay.
So DistillBERT, which we mentioned earlier,
Right.
is a student model that was distilled from BERT.
Okay. So it's like a compressed version of the original model.
Exactly, yeah. It's like a more compact version.
Okay.
And then there's quantization,
Quantization.
which is where you reduce the precision of the model's weights and activations.
Okay.
So instead of using 32-bit floating point numbers, you might use 8-bit integers.
Okay.
And this can significantly reduce the memory footprint and the computation time.
Right, because you're using less bits to represent the same information.
Exactly.
Okay.
And then there's ULMAN-X and ONNX runtime,
On NX.
which provide a standardized way to represent and execute machine learning models.
Okay.
So you can convert your transformer model to ONNX format,
Okay.
and then you can run it using ONNX runtime, which is optimized for different hardware platforms.
Right. So it's like a way to make your model more portable and more efficient.
Exactly.
Okay. So that's efficiency.
Yep.
Another challenge that the book addresses is dealing with situations where you have very little labeled data,
Right.
which is often the case in the real world.
Yeah, labeled data can be expensive and time-consuming to collect.
Right.
So you might only have a few examples or even no examples at all.
Right.
And the book talks about techniques like zero-shot learning,
Zero-shot learning.
where you try to use a model that was trained on one task to do a completely different task
Okay.
without any fine-tuning on that new task.
How is that even possible?
So it's about framing the new task in a way that the model can understand.
Okay.
So, for example, you might have a model that's trained on natural language inference,
Okay.
which is the task of determining if one sentence follows logically from another.
Right.
And you can use that model for text classification
Oh, okay.
by phrasing the classification problem as an inference problem.
So you're basically tricking the model into doing something it wasn't explicitly trained to do.
Yeah, it's about being clever with how you use the model.
Right.
And then there's few-shot learning,
Few-shot learning.
where you give the model a small number of examples for the new task,
Okay.
and it can use those examples to learn how to do the task.
Okay.
And there are also techniques like data augmentation,
Documentation.
where you artificially increase the size of your data set
Okay.
by creating variations of your existing examples.
Right. So you're making the most of the limited data that you have.
Exactly.
Okay.
And then there's the idea of using embeddings from large language models.
Embeddings.
So you take a bunch of unlabeled text,
Okay.
and you can use a large language model to generate embeddings for each piece of text.
Okay.
And then you can use those embeddings to do things like nearest neighbor search.
Okay.
So you can find similar pieces of text,
Right.
even if you don't have any labels.
So it's like a way to find relationships in the data without having to explicitly label everything.
Exactly.
Okay, so there are a lot of really creative ways to deal with limited data.
Yeah, it's a very active area of research.
Okay, now let's talk about the future of transformers.
Right.
Because one of the trends that we're seeing is this push towards bigger and bigger models.
Yeah, the models are getting huge.
Yeah.
Billions or even trillions of parameters.
It's mind-boggling.
Yeah, it's crazy.
So what's driving this trend? Like, why are people building these massive models?
So the main reason is that bigger models tend to perform better.
Okay.
They can do more things. They can understand language more deeply.
Right.
And they're also better at few-shot learning,
Okay.
which is really important because it means you can adapt them to new tasks with less data.
Right.
And there's this idea of emergent capability,
Emergent capabilities.
which are abilities that only appear in very large models.
Okay.
Things like improved reasoning
Okay.
or the ability to follow complex instructions.
Right. So it's like the model develops new skills as it gets bigger.
Yeah, it's like it unlocks new levels of intelligence.
Right.
And the book talks about the bitter lesson from AI research,
Bitter lesson.
which suggests that the most effective approaches are often the ones that are most general purpose.
Okay.
And that scale really matters.
Right. So it's not about trying to hand engineer super clever algorithms.
Right.
It's about building large, powerful models
And giving them lots of data.
and letting them figure things out.
Exactly.
Okay, but scaling up these models is not without its challenges.
Yeah, there are definitely challenges.
Yeah, like you need a ton of computing power.
Right.
You need a ton of data.
Right.
And it's also harder to evaluate these models and to deploy them.
Exactly. Yeah, it's
Yeah.
not just about building the model, it's about the whole infrastructure around it.
Right.
And the book talks about scaling laws,
Scaling laws.
which describe how performance scales with compute dataset size and model size.
Okay.
And these laws can help researchers make decisions about how to allocate resources.
Right, so you can kind of predict how much improvement you'll get if you invest in more compute or more data.
Exactly.
Okay.
And then there are techniques like gradient checkpointing,
Gradient checkpoint.
which is a way to trade off compute for memory,
Okay.
and distributed training,
Distributed training.
which is where you train the model on multiple GPUs or even multiple machines.
Okay, so you're basically parallelizing the training process.
Exactly.
Okay, so there's a lot of engineering that goes into making these large models work.
Yeah, it's a very complex process.
Okay, so we've talked about the present and the challenges of scaling up.
Right.
Now let's talk about the future.
Right.
What are some of the exciting directions that transformer research is heading in?
So one area of research is improving the efficiency of the self-attention mechanism,
Okay.
especially for very long sequences.
Right, because self-attention can be computationally expensive?
Yeah, it can be.
Okay.
So there are techniques like sparse attention,
Sparse attention.
where you only attend to a subset of the tokens, and linearized attention,
Linearized attention.
which is a way to make the computation more efficient.
Okay.
And then we're also seeing transformers being applied to new domains,
Okay.
like computer vision,
Right.
with the vision transform,
Vision transform.
which
Okay.
treats images as sequences of patches.
Okay, so instead of processing the image as a whole,
Right,
you're breaking it up into smaller pieces
exactly.
and then processing those pieces sequentially.
Yeah.
Okay.
And there's Tapas,
Pass.
which uses transformers for question answering over structured data like tables.
So it's not just text anymore.
Yeah.
It's any kind of data that can be represented as a sequence.
Exactly, yeah. The transformer architecture is very versatile.
So it seems like the future of transformers is very bright.
Yeah, I think so.
There's a lot of potential for them to revolutionize not just NLP, but many other fields as well.
Yeah, I agree.
Well, this has been a really fascinating deep dive.
Yeah, it's been fun.
We've covered a lot of ground.
We have.
And I think we've given our listeners a good overview of what transformers are,
Right.
how they work, and what they can do.
Yeah.
And I think the key takeaway for me is